You, Ariel and Eran, for this marvelous conference. It's really showing amazing things and really beautiful and amazing. And I would like to take you to one method of fabrication, which is gaining a lot of interest during the recent years. Shani talked a little about that. Printing started about 500 years ago by Gutenberg. When I give this lecture, I'm usually attacked in China because they said, forget it, we were the first. So let's stick to the European tradition. And we talk about Gutenberg, who invented the first printer in 1445. And this is the replica of his printer. That was very simple, now we say it's simple, like a kind of a mold of letters. And this was the first time that you could actually make one document again and again and again, and it will always be the same document. So beyond the technological effects, it also has societal effect. For example, you could print a template in Russia, and in 1 day or 3 days it would reach. Sorry? And the first printed document was the Gutenberg Bible. Those of you who are in Mainz, Germany, can see that Bible. Since then, not too much has changed. Maybe we can make better colors, better resolutions, faster printing process, printing on exotic materials, but nothing really changed. We talk about taking an ink, which is a colorant, place it on a substrate. The substrate can be a shirt, can be a floor, can be a wall, and you get a book, a newspaper, a shirt. For example, this printer that we see here is quite a common printer, digital printer, that is called inkjet printer. Most of us have at home such a printer. It costs almost nothing, but what costs a lot? The ink, which is good for us because we develop inks. So what I would like to show in this lecture, some work that we've done over the years in making shape morphing or actuation of materials. We use many of these approaches for making soft robotics, inspired by elephant trunks, etc. But I will show you how we can utilize various mechanisms to cause movement or morphing of objects. So we combine development of new materials and with different or various printing applications. For example, what happens if we print two materials layer by layer while they have different thermal expansion coefficient? So we have, imagine a plastic sheet, and on top of it, we have another sheet that is linked to it very strongly that has different thermal expansion. If we heat it to a specific temperature, due to the differences in thermal expansion, we will have bending. So how can we heat such an object? For example, we make an ink made of carbon nanotubes. This is very light material that you can put electrical voltage and it will get heated. So we can have a thermal object. Here you see printed carbon nanotubes on a plastic sheet of polyimide, but can be on anything. This is a thermal image, and you can see how this thing is heating up. So based on that polymeric substrate and printed carbon nanotubes, we can get deflections. And we can control the deflection, for example, you can see here, by combining electricity, carbon nanotubes, and polymers. We can also put the material that is called a shape memory polymer, and this is a material that can retain its shape. So we can cause movement of a snake. You can put a tiny camera at the end of this, and it can sneak to a drawer. Or, as a result of a collaboration with Bezalel student Shir Senior, he made electrical flowers. So you can control, by shaping the structure, you can make different shapes and different movements. We'll come back to flowers a little later. I see that Maya Van David is here. We have a very, very fruitful collaboration with Bezalel for many years that Maya and Dov are leading. And in this program, master students from Bezalel come and actually spend some time at our labs. Eran is also part of that, and we have other professors, and the results are really amazing. So again, we saw bending of carbon nanotubes. We can make also grippers that are working under magnetic field. For example, if we make magnetic material, and in this magnetic materials we can make alternating magnetic field, the friction will cause local heating. If we have heating, again we will have bending and so, and you can see here a smart gripper that can take out a very light weight. Since we're in a very small audience, I can tell you a secret. With ionic strength, electrical field, magnetic fields. So in some of the lectures we already saw some changing of objects, natural objects or flat objects. But we can actually make 3D objects that will change with a specific trigger. One of my favorite printing technology is a very simple one called DLP printing. You take a liquid bath that contains monomers and photoinitiators that will make a liquid to become solid. Liquid will become plastics, but only at a specific place. So we shine light from below or up, depends on the printer, and we print a 2D image. The shining or radiation of a specific image is done by the same barcode that we see here on the roof. This is the macro mirrors. By using that, we start with the liquid and we move into making an object that will come out of the liquid. Very simple process, but you need to know how to design the materials to do that. And we have designed a variety of objects. For example, this is sponges, elastic sponges. This is a smart gripper that can hold delicate things. We can also print objects that are filled with a liquid, magnetic liquid called ferrofluid. So we can put magnetic field below, and we have a crawler. Or we can use a material that is called shape memory polymer. This polymer has a kind of a memory, better than mine, I guess, that it remembers what was it in the past. Anyone can guess what's this? Eiffel tour. So we printed the Eiffel tour, we squeezed it, and then let it go to a specific temperature that we tailor and get again the structure. Here, this is a tube, more like a stent. We hope that we can make it to the field of biomedical field. This is a stent printed in a very specific dimension to fit a specific patient, then squeeze it, put it in the vein, and then it will go up to the original work. This work was done together with Professor Daniel Cohen. As part of collaboration with people from Bezalel, one of the students saw the work that we do with shape memory polymer and decided to make shape memory flowers. So the flower is composed of the shape memory. Once you go to the sun hits this flower and it can open up. This was done by Shira Eliezer. Another student, the student Atara Seltzer, made smart shoes. This is a typical shoe that you go to work. In the evening you come to the hotel in a conference and you can go to a party. So this is by simple heating, by hairdryer. But we can also go one more step and we can make object that can function as something. For example, imagine this box, that you fill in this box something and you heat it up, you can open the box, and since we have two different types of materials that respond at different temperatures, we can open and close the box. As you can see here, not here, a second. this is a box put in hot water and it opens up. So it can release its content. And here, we coated, you remember the carbon nanotubes? They are black material, and what happens to a black material when it absorbs light? It gets warm. So we can remotely activate the opening of the box by shining light onto it. There are other materials that can get heated by shining light. For example, gold nanoparticles. So we made gold nanorods that can absorb the light only at a very, very specific wavelength. And we made a gripper, this is a reverse gripper, that can open up upon shining of light. So this is remote activation of the structure. So these were all plastic material, polymeric materials. We also work on hydrogels. So this is work done by Ayala, for example. This is gelatin that you can eat. And we have developed several technologies to make hydrogels. We also developed new photocatalysts that can work in water. So once we knew how to make the hydrogels, we took it to an interesting field that can be new drug delivery systems. And the idea is to combine the structure with the release of a drug. So we can make hydrogels. Imagine that the future shape of the pill will be patriotic drugs or something else. This work was done with Professor Magdassi, and it is based on opening or expanding or swelling under water, for example. So in this case, we have a printed hydrogel, put it in water, and it expands. We can control the shape of the hydrogels, and it can release a drug or can swell in a different way, simply because we combine the properties of the hydrogel together with the shape of the hydrogel. Or you can make quite smart drug delivery system in which you take a pill, and when you swallow it, it reaches the stomach, which is pH 0.12. It is closed. When it goes to the intestine, the pH is 7.5. Then it expands, and it can start releasing whatever is loaded. Again, making change in structure based on pH and water. So, since Shani gave a good introduction about printing of wood, I will talk only about one aspect of the printing of the wood, that is making, this led actually to the formation of the company Daika. This is a work that we've done together with Eran Sharon and Udet Shosev that is related to the problem that is called wood warping. When you have a wooden chair sitting in the sun and under the UV and the humidity, usually it warps. So we wanted to imitate the warping process, and the idea is that the warping is caused because different directions of the fibers that are within the wood. I will not go into the details here, but we could control the twisting or the warping process by controlling the direction of the printing. And here I'm going to show only a few examples that you can actually tailor how the wood will transform to which structure. In here you see helices, you see the pitch that we can control simply by making a specific design of the printed wood. So I usually try to see also what is it good for. So what I've shown here can be good for, and I believe that some of the work shown by the previous speakers, in various fields, including soft robotics, smart grippers, biomedical grippers, drug delivery, optical waveguides that can change shape or change the transparency. Architecture, we've heard adaptive antennas, imaging an antenna that is closed, and when you go to space with the satellite, it will open up and will go to its full size. Or window shades, like shades that can open and close simply by following the sun, like the sunflower seed chamaniyot. And also we can make solar cells that follows the sun. So I hope that I convince you that combining printing brings a unique tool once you know to control the materials. And what's next, I really don't know. What I tell my students is dream, print your dreams. So I'd like to thank you. This is Shape Memory Polymer. I would like to thank you, and of course, funding agencies and the students, the specific students who work on the very closely related work in this field. Thank you very much.
Thank you very much, Shlomo. Fascinating talk and direct continuation.